Everything starts out as a 1s2 except what? Hydrogen, which is 1s1. Now we're down to a 2s1s2. All right, so that's a 2s2. Then a 2p6, a 3s2, and a 3p4. All right. You guys see that? Is that what you got? Wonderful. All right, let's do the next one. Nitrogen. All right, that's a 1s2, 2s2, 2p, 1, 2, 3. How did we do there? Yes? Okay, and then one more is calcium. Is a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. How do we do on that one? Good?
You've been doing this a while.
You mean you wasn't that quick? All right, so is that good with everybody? Now let's look at what these things mean, okay? The valence electrons. How many valence electrons does sulfur have? Well, what you have to do is you have to say, okay, this is a 1, this is a 2, a 2, a 3, a 3. What is the highest number? 3. All right, that means you got to count all the electrons in the 3s, which means what? 6 valence electrons. So if you were sulfur and you wanted to do chemistry, you have 6 electrons that you can play with. They can be shared, they can be transferred, and we'll talk more about that later. They can somehow be tinkered with. All right, did somebody just do that? Pop their lips? Oh, okay. So now here, this is a 1, a 2, and a 2. What's the highest level there? A 2. How many electrons is in that highest energy level? 5. So that means that this thing has 5 valence electrons, which means what? Nitrogen has 5 electrons that can be either lost or gained or shared to make normal chemistry happen. All right, what about calcium? How many valence electrons does it have? 2. Now this is a cool thing about the periodic table. Let's just look at calcium. Calcium has 2 valence electrons. Well, how many do you think magnesium has?
1.
2. How many do you think beryllium has? 2, 2, 2, 2. All right, look at your periodic table. Do you see a 2A written above that column? That means everything in that column has 2 valence electrons. See, that's why everything in a periodic table, up and down from each other, reacts similarly. All right. Now, how many electrons does all this mess have here? 1. Forget about it. We'll talk about that in a minute. How about here? Boron, aluminum. How many valence electrons? 3. How about here? All right, nitrogen. Look at nitrogen. How many's that got? Well, is that unexpected? 6, 7, and 8 here except for helium, right? How many valence electrons helium got? 2. Yeah, it's a 1s2. So everything except helium has 8. All right, are we good? Valence electrons. So very quickly, without doing the electron configuration, I would say, well, how many valence electrons does selenium have? And you would say, boom, just like that. You see, there's reasons for that when we draw the Lewis dot structures in the next couple of chapters. But you kind of have to show where it comes from, I think. You have to know where you're coming with that. And it's coming from the electron configurations. You pick the highest numbers, and that's the way it goes. All right, yeah?
Does that mean it's the outside shell?
That's right. That's the outside level. That's where the contact is going to be taking place. All right. Is there anybody tore up about this? Okay. Noble gases are very unreactive. Everything likes to be like a noble gas. Yes? How many electrons are in a noble gas? 8. Well, there's something called an octet rule. And that says that everything wants to behave like a noble gas. So how many electrons does fluorine have? 7. How many would it love to have? So what would it need to do? Strip one off of something, right? So anytime you got fluorine sitting around, if it comes into contact with anything, it's a wonderful electron scavenger. It will rip the electron right out of there and keep it. All right? Why? It will. Like if you release fluorine in the room, your eyes will immediately start burning. Right? Have we already talked about this? Your eyes will immediately start burning. Why? Because that fluorine will go to your eyes and take electrons. Period. All right, that's what's called an electron scavenger or an oxidation reduction reaction. All right, and that would be bad. That's bad. Now what about chlorine? What would chlorine do? Same thing, but at a little lesser degree. All right, so do you know what makes something colored? What makes something colored? Does anybody know? Your electrons. Your electrons. There are there's 2 types of dyes. There are inorganic dyes that have these transition metals in them, and they have different d electrons, which we're about to talk about in a moment. See, this is the d block. When light hits them, they have different colors. And see, inorganic synthesis people who works in transition metals, a lot of times their labs are very pretty. They have wonderful yellows and fuchsias and blues and all sorts of compounds, greens and purples. And the reason that they do is because these electrons here are interacting with the light stream. That's one way you get color. Electrons. With me? What's the second way you get color? In organic dyes. Okay, now an organic compound, remember, contains carbon and hydrogen. All right. So maybe you've got a whole length of these carbon and hydrogen bonds here. Well, as these electrons and these conjugated systems, that means double bond, single bond, double bond, single bond, as they move back and forth, it makes color. A perfect example is ketchup is red. What's the compound in ketchup that makes it red? Tomatoes. Stop it. Of course tomatoes. It's lycopene. All right, and the lycopene is one of these conjugated enes, and it reflects light in such a way that it makes color. Okay, so what happens if I take chlorine bleach and put on my shirt? What color does it turn? White. Why? Chlorine's an electron scavenger. It will find the electrons in that dye and take them to be like argon. Does that make sense? And guess what it's going to leave behind? No color. You with me? All right. Now, this works the same way when you kill bacteria, right? Chlorine gets next to the bacteria cell wall and or membrane, and what does it do? Rips electrons right out of there, thus killing the microbe. All right. It's all got to do with what's called the octet rule. Everything wants to have 8. Why the magic number 8? I don't know. It wants to have 8. All right. Is everybody cool with that? Okay, now here's one more thing. People talking about a shortcut. All right. Take the noble gas that comes before sulfur. So here's sulfur. What is the noble gas that comes before sulfur? Neon. All right, now start from neon and tell me the electron configuration. 3s2? 3p4. Now what have I shown? I've shown a neon core and valence. You with me? Well, what's the most important thing? Valence. So why would you write all this menagerie? And the answer is you really wouldn't. You use your shorthand notation, right? Of course, you have to teach the longhand notation first so you know what's going on. What's the shorthand notation here for this nitrogen? What's the noble gas that comes first? Helium. And then there is a 2s2, 2p3. Again, what are we showing? Valence electrons. What about calcium? What's a noble gas that comes